Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing sediment data, specifically the options in the options menu. So let me show you what I'm talking about here. I've got my HEC RAS open right now. If I'm going to edit some sediment, I'll go up to edit sediment data, and then in this options drop down right here, this is what I'm going to be talking about in this lesson. All of these options from user defined grain class all the way down to the bottom to observed data. Okay, if you want to follow along in the user's manual, I've got the link to it right here. I will leave a link to this page in the description of this video. This is just the first page, but I'm going to be talking about the sub pages here, which is define grain class sediment properties, all the way down to observed data. Okay. All right, let's go ahead and get started. So like I mentioned, this is the interface for sediment data. You can get there by going edit sediment data, or you can click on this button right here. It's the cross section with a little water SED in it, and we're ready to rock and roll. Just as a quick introduction, I've already covered the contents of this first tab, initial conditions and transport parameters, in lesson 53. And then last lesson, lesson 54, I covered the boundary conditions. Yeah, that's this tab right here. So if you're interested in those topics, check out those videos. But once that data is defined or before, go ahead and click on options and let's get into it. All right, the first option here is user defined grain classes. So when we select this option, we now see our 20 grain classes here with the number, the label, and then some numbers over in the other columns like the minimum size, the maximum size, so that's the range, then the mean, and then SG is specific gravity. If you forget what they are, you can actually click on that column and it'll say specific gravity down here of the grain class. N is porosity or nu, and then UW, that is the unit weight in pounds per cubic foot. COH, that is cohesion. So if this particular grain size has is cohesive or not, one I believe is true, zero is false. And then this last column here, DE, refers to the effective settling depth. So the user is allowed to define their own grain classes to be used for the grain size distributions. What you can do is change these numbers. For instance, if I wanted the minimum value for clay to be less than 0.002 or more, I could just change it, and now it's 0.001. Now the max right here, if I wanted to change that, I could change that to 0.005 instead of 0.004. So if I click OK and then go to define a gradation, now clay is defined as the new numbers, the new range for 0.001 to 0.005, and that's in millimeters. All right, so you may realize that there's now a little bit of overlap. If I go back to that option, now there's overlap between the maximum clay and then the minimum very fine silt. That's what VFM stands for. But to reduce this or to prevent this from happening, what you could do is just, let's change this back real quick, and okay. And then click this checkbox down at the bottom to enforce adjacent non-overlapping grain classes and a geometric mean. So let's go ahead and click that. Now what it does is it disables the minimum fields, except for the very first one for clay. And this 0.004 will automatically be updated with whichever value I type in here for the maximum size of clay. So now I'm going to go 5, hit enter, and then that value updated. Now down here, there's a label that says currently customized. That means that the data in here is no longer default. It's been changed by the user. If I want to reset the default, there's a button down here that says defaults. I'll click that, and then boom, the numbers have been updated. There must be at least 20 grain size classes, and that's the 20 that you're seeing here. Something else that you could do is, if you uncheck this checkbox, is you could make two grain classes have the exact same minimum and maximum, and then change the name, I believe. Yeah, so you can change the name to whatever you want. And there's probably a good reason to do that, a use case, but I just can't think of why someone would do that at the moment. Right, so I'll click default. That's been reset, and we're back to where we started. All right, so let's click OK and move on to our next option, that is set cohesive options. So what we have here is starts off with 3 radio buttons. So this is in the same group, so only one can be selected. By default, what we're doing here is using the selected transport function for all grain sizes. So what that means here is this transport function that's defined on the initial conditions and transport parameters. Currently, Acker's white is selected, but there's other options. This is going to be the method to dictate the transport of all 20 grain sizes. So if I go back to set cohesive options, and I wanted to control the smallest 5 grain size classes differently, I can click on one of these second or third radio buttons, use the Crony or Parthenotis for clay and silt size fractions, or the HEC 6T capacity method. And then what you do is specify particle erosion data and mass wasting erosion data in these fields right here. So for instance, there's this threshold here. This is, I believe, the critical shear stress, tau sub C. And then you have shear stress based on the simulation data. So if that simulation shear stress equals the critical shear stress, the quotient equals 1 on this plot, and that's sort of the sweet spot where you have no deposition and no erosion. If the shear stress is less than critical, you'll have deposition, and if it is more than critical, there will be erosion. Some of the typical numbers that were mentioned in the user's manual is 0 0.2, 0 0.6, 1.6, and 15. And there's also 2 different forms of excess shear equation. This is the first one here that uses M. M is dimensionless, and then the K sub D is dimensional equations. There's a few other parameters in this options dialog box for cohesive options that pertain to the 2D option, like over here. And I'm just covering 1D right now, so I'm going to have to come back to the 2D options in a later lesson. All right, so let's go ahead and click OK, move on to the next option. That is the bed change option in 1D. This pertains to which parts of the cross section receive erosion and deposition, or I should say are susceptible to erosion and deposition. At the top, we have this 2x2 matrix for the channel and the overbank, or it's called floodplain partition, but it's called overbank down here. Channel, channel, overbank, overbank. We'll talk about this table at the end, but up here, this is the global parameters. This is probably what you're going to be using. And what it is the channel and the overbank deposition and erosion. What you're seeing here is the most common situation where the main channel is susceptible to erosion and deposition, and the floodplain partition is not, or the overbank is not. Let me bring up the user's manual here and go to the page where it talks about this. And if I scroll down here, these plots are really good, I think. A, B, C, and D are the 4 scenarios that it's giving us. And those are ranked from most common, which is default, to the least common, almost never. So the most common is the default. These are the values we saw. Veneer for both channel deposition and erosion, and then none for overbank. And as you see from the diagram, red represents the erosion, that's material removal, and then the yellow or the tan represents deposition, where there's added material. For this overbank, there's no bed change, there's no deposition, and there's no erosion. Okay, B, that's the next most common. That's basically the same thing for the main channel, but the overbank has deposition. There will be some deposition on the overbank. C is rare. That's where you're going to have both deposition and erosion on the overbank. And then D here represents almost never. That's where you have no deposition on the overbank, but you would have erosion. Also take note that the yellow dots don't represent the bank station of the channel. It represents the sediment bank station. Hold on. I forgot what it was called. I'm going to go ahead and add some numbers to my diagram. This is river station 5000. I'll say it's 3 feet of depth, and I'll use the bank. Yeah, so it's this yellow dot here, sediment bed station. This is what is defining the channel versus the overbank when we look at that option for bed change options. So we have channel here, and then we have floodplain partition, or overbank, if you will. Okay, and that's defined by these yellow dots, not the red dot. At the moment, these 2 dots do overlap. The sediment bed station is at the bank station, and that's most likely what is going to be the case, but not necessarily always true, because I can move the sediment bed station to different locations. All right, let's go back to the options now. Notice that these are drop downs, and it's not just none or veneer. There's also some reservoir related options you can specify. So there's some reservoir here. And then simplified CEM, this is also for like a reservoir removal. CEM stands for the Channel Evolution Model for Dam Removal and Reservoir Drawdown Models that need to form channels in broad depositional environments. The user manual talks more in depth about this topic, but I just wanted to mention that in this lesson. It's a little bit too detailed for what I want to do here today. Lastly, this table down below here allows the user to specify these values up here, but not on a global scale, on an individual cross section. So what you do is you select your river, and then you select your reach. Right now I've got River A, Reach 1 selected. Here are my cross sections. So I could go ahead and specify veneer and veneer for the main channel, and then overbank would probably be none and none. This is the default value, as well as a few other parameters such as the max width, side slope, center station, and then the left and right deposition stations. So there's lots of detail that can go into this particular bed change options. All right, the next option is going to be transport methods. So this is divided into 1D methods at the top and 2D methods at the bottom. I'm going to skip over 2D and just talk about the 1D methods. So right now, the routing method is the default is continuity. Actually, I changed it, but there's also a limit water velocity. If the conditions are just right, it's possible for sediment to move faster through the water than the water itself. So to prevent that from happening, you may want to change this first option to limit to water velocity. The next line down here is sediment junction split method. Now, right now, there's either flow weighted or potential weighted. The default is flow weighted, but you can also select potential weighted. And what this refers to is if you go to your boundary conditions and you have a junction, if this junction is not defined, then the default that we just looked at in the option is the method that HEC RAS is going to be using during the simulation. So that's either the flow weighted method right here or the potential weighted method right here. What these mean exactly, I describe in more detail in the previous lesson where I talk about boundary conditions, and that's lesson 54. So check that out if you're interested. Lastly, here is pool pass-through method. Our options are upstream capacity or upstream and lagged downstream. This pertains to how sediment is routed through a reservoir. So if you go with upstream capacity, this tends to trap more sediment than the other method. And if the incoming load exceeds the upstream transport capacity, then the excess sediment is deposited. The other option, upstream and lag downstream. Using this option, the sediment that's leaving the reservoir pool is influenced by the sediment transport capacity downstream of the pool, but with a time delay or a lagged response. All right, so next up for our options. So 2D options is grayed out for me. And then B-stem options, I believe this pertains to the optional tab right here. There is a link in the manual to the page that describes this more, but I was just going to skip over it. Okay, lateral weir options right here. So I do have a weir in the model. Right here, it's highlighted. It's at River Station 2800. So I'll click on lateral structures. Here's my lateral structure. It has a gate and it has a weir, just so you know that there is a weir there. So you need at least one weir in your system if you want to see this dialog box. So I see one row, and this is my River A, Reach 1, River Station 2800. The default value here is flow weighted, and what that means is the quantity of sediment that's going to pass through the weir is going to be by default proportional to the total flow through the weir. However, that's not likely always the case because certain particle sizes will be too heavy to get up over the weir, since the weir is typically towards the top of the water or closer to the water surface. And for that reason, the user can specify the specific grain class as the maximum grain size class that can pass through the weir. So for instance, if I clicked right here, this is FS, I believe that's fine sand. If I make this selection, that basically means that fine sand and every particle size larger than fine sand cannot pass through the weir. You can change that to any of the 20 grain size classes, but again, the default is flow weighted. All right, next up, options, bed mixing options. The capacity partitioning method right here, this deals with how total sediment transport capacity is distributed among different grain size fractions. So if we go with the default here of bed gradation only, this only considers the bed gradation. But if we select the weighted with load method, this considers the bed gradation and the incoming sediment load. Further down, we have active layer options. This is the active layer thickness. Active layer is the topmost sediment layer that actively participates in erosion, transport, and deposition. Right now it's set to D90, but it's more common to multiply that D90 size of the grain size distribution by a specific multiplier, like 5 times the D90 size. 1 through 5, values of 1 through 5 are typical for gravel riverbeds, but values larger than 10 are more standard for sand riverbeds. This is where HEC RAS allows the user to define the active layer thickness in multiples of the D90 size. If the active layer tries to fall below a minimum thickness, which we can define right here at, say, half a foot, then the active layer will be set to that minimum thickness. And finally, the last bed mixing option here is the cover/active layer gradation. Say, for instance, your river station has a specific gradation, but on top of that, you have armoring. Then that armoring could have its own specific gradation. And this right here is where you make that assignment. So what you'll do is click this checkbox for specify separate cover/active layer gradation. And then you're going to select the river, you're going to select the reach. And then after that, you're going to select what is that gradation, as well as the layer thickness right here. So you'll have a separate gradation for that armor that'll be on top to a certain thickness. And then below that, you'll have the actual gradation assigned to that river station's cross section. All right, we're doing good, guys. Next one is options, subsidence. Subsidence is when the elevation of the cross section decreases in elevation compared to a vertical datum over a long period of time. So you would go ahead and for each river and reach, you'd specify for the cross section what is that rate of subsidence. This is probably more likely to come into play for longer simulations because the rate of subsidence is not particularly fast. All right, next up is options and set pass-through nodes. We have both standard and pool. Whichever you select, you're going to then go ahead and select the node type and then specify the river, specify the reach, select the cross-section, and click OK. So what I just did there was I specified that this cross-section at River Station 4000 will be immune from all erosion or deposition. This feature allows the user to specify certain cross sections where there is no erosion or deposition. So, for whatever reason, you just may want to prevent erosion or deposition within your HEC RAS model. This is the way to do it. All right, last one here, options and observed data profile. In HEC RAS, observed data refers to the measured real-world data that is imported into the model for comparison against simulated results. So this is how users can calibrate and validate their models using observed data. To do that, you're going to go ahead and click this button for Add Observed Profile. And then what we do here is we can specify the date and time, create a new variable, or use an existing variable. Let's go ahead and just create a new variable first. So I'll just say like new var1 and then click OK. What it did is it gave me this new column in the table for new variable 1, whatever that actually pertains to. Let's actually use a predefined variable that's part of HEC RAS now. So I'll click Add Observed Profiles, and then now I'm going to select Invert Change. So when I select Invert Change and click OK, I've got a new column here for Invert Change. All right, let's do another one. Here I'm going to go with Invert Elevation. So I'm just going one at a time here. This time I'm going to specify a date and time. So I'm going to say January 2020. And then if I click OK, now we have a specified date and time associated with that variable. I did want to point out that there are a lot of variables here. So if you scroll down, you see your common 1D results, 1D hydraulics. I'm scrolling down 1D cumulative control volume terms and so on. So there's all the values or the variables that you can specify observed data for. One last visit to the user's manual shows a better example of this observed data. Here we have the long cumulative volume change total. And what we have here for values are negative values at the top of the reach and then positive values towards the bottom of the reach. So what that tells me is that there is observed data here that says there's erosion here and then downstream there is deposition. As far as using that observed data is like a plot right here, for instance. You can have the model results be this solid black line here, and then observed data could be the red dots that are also connected with a line. So this data looks like it matches up pretty well here. And that's the purpose of observed data is for, like I said, calibration and validation. All right, well, that was it for this lesson. We talked about sediment data and then talked about the different options that are available from this options menu.